I'm sharing my screen. So today we'll discuss about the um, test bench for the sequential circuits. Okay. So test bench. So introduction to the sequential circuits. How to write the code for sequential circuits and test bench for the sequential circuits. Okay. So so here so first introduction to the sequential circuits we'll see. So if you see the sequential circuits, you have first we'll study about the latches and flip-flops. So latches are nothing but level trigger and flip-flops are nothing but edge trigger. First I will write the code for the basic D flip-flop. Okay. So if you see the basic D flip-flop, you have the input D and let us take the passage of clock. Okay. And next you have Q and this is Q bar. Q and Q bar. Okay. So this is D flip flop. This is my D flip flop. Okay. How to write the code for this D flip flop? Module, module, and my module name D underscore flip flop, and you need to declare the inputs and outputs. Okay. One more reset is also there. Okay. Reset is active high reset. Okay. Active high reset. Input. I'm initializing clock reset and so this is let us take d underscore in. Okay, d underscore in and this is small q and small q bar. Okay, so so input is d underscore in and outputs are, so you need to declare the output. Okay, so you can declare within the bracket itself. Okay, so here I'm declaring. One second. So d flip flop input clock reset d underscore in and output q and q bar, okay, q and q bar. So next I'm using a this always block, always at the rate passage of clock. Okay, always at the rate passage of clock. So that means this is a synchronous reset. Okay, so begin uh, so if reset, that means if reset equal to 1. Okay, begin q is non-blocking with 0 and q bar is non-blocking with 1. Okay, q bar is non-blocking with 1 and end. Okay, else begin. Okay, here else else begin. Okay, else begin q equal to what, just here I'm continuing. Q is non-blocking with d underscore n and q bar is non-blocking with the not of q, not of q, end and end module. So you know that D flip flop is a sequential buffer. So here uh, so suppose if whatever the D input is there, you are getting at the output during the passage of clock. Okay, so this is a synchronous reset. Okay, synchronous reset means both when it is going from reset mode to functional mode or functional mode to reset mode. Okay, so both are synchronous with the clock. Okay, that I will tell you, that I will explain you with the waveform. Okay, synchronous with the clock. Suppose if you are using asynchronous asynchronous reset. Okay, asynchronous reset means how to do means you need to write always at the rate if I am using active low reset. Okay, if you are using active low reset, so asynchronous always at the rate passage of clock or neg edge of reset. I need to use neg edge of reset. So negative of reset. Like this, you need to use a in place of this D flip flop. Okay. So this is asynchronous active low reset. Asynchronous active low reset means when it is so when it is low, that is activated. So when it is high, that is deactivated. Okay. So when it is going from reset mode to functional mode, that is synchronous with the clock. Okay. And when it is coming from functional mode to reset mode, that is asynchronous with the clock. Okay. So why you are using this asynchronous active low reset in the industry? Mostly you are using asynchronous active low reset only. Suppose like your design, sometimes if you want to reset the circuit, okay, uh, so your clock is not working. Okay, you can't reset now. When it is synchronous with the reset, when your clock is not working, you can't reset. So that's why when it is going from reset mode to functional mode to reset mode, okay, so that is asynchronous with the clock. Okay, that is nowhere depending on the clock. Directly you can reset your design. Okay, so that is asynchronous active low reset. That too you are using active low reset. Why active, not active high reset? Means active high means what? So when it is going from 0 to 1, okay, this is deactive and this is active. Okay, so you are operating your device uh, on means when the reset is high. Reset is high. Okay, so that means you are applying extra power to operate your device in reset mode. Okay, so normally your cell phones are there. Cell phones when you switch off, so that means all the circuits will be go into reset mode. So when reset equal to 0 only, then it will go to the reset mode. Okay, so why we need extra power to, that is you are giving one to operate your circuit in reset mode. Okay, so that's why we are using active low reset. Okay, that to asynchronous active low reset we are giving. Okay, so here so the reset will be like how it will be there means, so synchronous reset means, synchronous let us take active high reset is there. Okay, active high reset. So how it will be there means, there is a D flip flop, and you have a mux over here. Okay, this output is given to D, and here this is reset. Okay, so when reset equal to, so you have two inputs 0 and 1. So when reset equal to active high, no, so that means when reset equal to 1, you are giving 0, and when reset equal to 0, this you are giving the input. Okay, so one more disadvantage of this synchronous reset means, in the timing analysis, you need to apply extra extra, you need to calculate the extra path for this mux also. Okay, so this is anyway clock is there. This is D flip flop, you have Q and Q bar. Okay, so this is synchronous active high reset. Okay, if it is synchronous active low reset means just it will change the inputs and outputs. Okay, so coming to asynchronous, let us take active low reset. Okay, active low reset. So how the circuit will be there means, you have D input and clock and Q and Q bar. Here there will be a bubble. This is nothing but clear. Mostly in the digital, you have preset and clear. These are nothing but asynchronous inputs. Okay, so when these are activated, when preset is activated, irrespective of this input and clock, it will force the output to 1. Okay, it will force the output to 1. Clear is nothing but irrespective of when it is activated, irrespective of input and clock, it will force the output to 0. Okay, so here what I am giving, that means asynchronous active low reset means I am giving reset underscore n. Okay, this is a nomenclature we are using in the design. So reset underscore n. So that is when reset equal to 0, it will reset the device. So clear will be activated and that output becomes 0. Okay, this is asynchronous active low reset. Okay, so this is about the reset circuit. Okay, and next uh, so next if it is yeah, so this is D flip flop. Okay, And suppose so 1 second. If it is SR flip flop, okay. So if it is SR flip flop, what you need to do? You need to use the if else statement. Okay. Suppose if it is the SR flip flop, uh, so or first I am writing the test bench for D flip flop. Okay. After that I will write the SR flip flop. So test bench for any sequential circuit. Okay. Any sequential circuit. So for the combinational circuits, you have 4 steps for the combinational circuits. No? In the test bench, first step is you need to declare the internal variables. Next step is you need to instantiate the design. Okay. And third step is you need to initialize the reg variables. And fourth step is you need to give the stimulus. Okay. You need to give the stimulus or input test cases. Okay. So that are the 4 steps. The same steps are there in sequential circuits only. There is one more step. You need to generate the clock. Okay, you need to generate the clock. Okay, I'm writing for D flip flop, test bench for D flip flop. I wrote the code, and next I'm writing the test bench. Okay, so module module D underscore TB. Okay, so this is my module name. So what is step one? You need to declare the internal variables. Okay, so declare the internal variables for the test bench. Okay, so according to port hole connections, whatever the top module inputs are there, that you need to declare with reg data type. What are the inputs for the test bench? Clock reset d underscore in. Okay, and next what are the outputs for the output variable for the test bench? You need to declare with y data type. This is q and q bar. Okay, so this is step one. You need to declare the internal variables. And step two, you need to instantiating the design in the test bench. Okay, so instantiating instance instantiating the design in the test bench. So there are 2 types of instantiation I told you in the port rule connections and instantiation. There are connection by name and connection by order with position list. Okay, here I am using connection by connection by position with order list only. So how the syntax will be there? Design name. So what is my design name? D flip flop. Okay. So design name is D flip flop only, no? Yeah, D underscore flip flop. Okay. So my design name is 1 second. And my design name is, yeah, my design name is D underscore flip flop. Okay. And instance name DUT design under test. How you declared the inputs and outputs in that design, that same order you need to follow. That is nothing but connection by order with position list. Okay, so here you given clock reset t underscore in output q and q bar, no, that same order you need to follow in the test bench. Okay, so clock reset d underscore in and q bar. Okay, this is connection by order with position list. With position list. Okay, connection by order with position list. Okay, and next, what is step three? Step three is you need to initializing the reg variable. Initializing the reg variables. So what are the reg variables? So I am using initial, begin. Okay, I am using concatenation operator. Reg variables are clock, reset, and d underscore in. No? So clock, reset, and d underscore in. Okay, I am giving to 0. End. Okay, I need to initialize the reg variables. Okay, Next, step 4, generating the clock. Generating the clock. Okay, how to generate the clock? You can use always or forever. So always I'm using a delay hash 5 clock equal to not of clock equal to not of clock. So that means clock equal to not of clock means what? So for 5 time units, okay, 5 time units, this will be half cycle, and one more, either it may be nanoseconds, depending on the time scale, whatever the time scale you are using. 5 nanoseconds, this is the half cycle, off time, and 5 nanoseconds on time. Okay, again, so this is till 10. So what is the time period? Total time period. So t equal to what? T equal to 10 nanoseconds or 10 time period. Okay. So total time period is what? Total time period. Total time period, that is equal to 10. Okay. So you know the duty cycle. So what is duty cycle? So it should be 50%. T on by T off plus T off into 100%. Okay, 100%. This is the duty cycle. So what may be the duty cycle? It is on for 5 time units and off, on for 5 time units and off for 5 time units into 100. Okay, so you are getting 5 by 10 into 100. So this is equal to 1 by 2 into 100. You are getting 50% duty cycle. Okay, so you need to select a clock, you need to generate the clock such a way that such a way that so it should be duty cycle of 50%. Okay, and step 5, driving your stimulus. Driving your stimulus. Okay, initial, begin. Okay, in order to avoid setup time and hold time violations, I'm trying to get the output in the negate of clock. Okay, during passage of clock when you take, so what happens means you will get some violations in setup time and hold time. So to avoid that setup time and hold time, I am using at the rate negate of clock. Okay, at the rate negate of clock. Okay, first I am reset. I am giving reset. Reset equal to what? 1. Okay, at the rate negate of clock. Negate of clock. Okay, reset equal to what? 0. Okay, at the rate negate of clock. You can give the delay also. So delay means hash 10 also you can give. Okay, for every uh, waveform you can give hash 10 also. Again, I am releasing the reset. Again, at the rate negate of clock. Negate of clock. So I'm giving first d underscore in equal to 1 tick binary 1, and at the rate negate of clock. Negate of clock, mm, d in d underscore in, that is equal to 1 tick binary 0. I'm giving the in means range, like these stimulus. Okay, so I'm giving the inputs for the test bench, input through the design through the test bench, and design will process and it will give the output to the test bench. Okay, and next end. Okay, end and end module. End module. Okay, so this is the test bench. Do you understood the test bench? Any doubts or queries? Shall I move forward about the design in D flip flop? What is the difference between synchronous and asynchronous count, asynchronous reset? Okay, asynchronous active low reset, asynchronous active high reset, synchronous active low reset, and test bench. There are 5 steps are there. First you need to declare the internal variables. Next you need to initialize the design in the test bench, and next you need to initialize the reg variables, and next you need to generate the clock with 50% duty cycle, and you need to drive the stimulus. Okay, first you need to assert the reset. You need to make reset equal to 1, as this is the like mm, reset So positive uh, positive edge trigger clock with active high reset. Okay, so that's why you need to assert the reset, and next you need to deassert the reset. You need to make reset equal to 0. So when reset equal to 1, it will be in reset mode only. All the outputs will be asserted to 0. Okay, and when you are deassetting the reset, when you are making reset equal to 0, so it will go from reset mode to functional mode. Okay, d in equal to 1 tick binary 1. I am giving the inputs to this d input. So whatever the input you are giving, that you are giving it into q. Okay, q is 1 means a q bar equal to 0. Q is 0 means q bar equal to 1 you are getting. Okay, is it fine? Do you understood this test bench? Shall I move forward? Anyone? Any doubts?
No.
Okay, one second. I'll show the codes, Verilog codes, and mm, flip-flops. Okay, flip-flops. In this flip-flop, okay. Uh, so I'm opening to Xilinx Vivado. Here, if you see the D flip-flop, one second, D flip-flop. This is D flip-flop we discussed. Okay. So this is the code for D flip-flop. So whatever the code I explained. Module D flip-flop, module name is D flip-flop, D clock reset Q bar, input D clock reset, output reg. If it is if it is behavioral modeling, you need to declare with reg data type. Okay, sorry, I forgot this. Okay, so output should be declared with which data type? Reg data type. You need to follow these port rule connections. Okay, so when it is this one, this behavior, we are using behavioral modeling. So this is reg data type. Okay, so this is reg data type, and next if reset equal to 0, begin, q equal to 0, q bar equal to 1, end. Okay, else if d equal to 0, begin, q equal to 0, q bar equal to 1, end. Else begin, q equal to 1, q bar equal to 0, end, and end module. This end is there, no? This you need to end and end module. Okay, this is the code for D flip flop. And coming to the test bench, this is the test bench. So here you can use that all. So you can use like this also, module D flip flop TB while Q and Q bar. So you need to declare Q with Q and Q bar with wire data type, and D clock and reset with edge data type. And next you need to instantiate. Okay, so my design is D flip flop, and instance name is insta. D clock reset Q bar. So this is what this is nothing but instantiation. Uh, so instantiation connection by order with position list. Connection by order with position list. Okay. Connection by position. Okay. Sorry. This is connection by position with order list. With order list. Okay. Order list. Connection by position. There are two types of instantiation are there. No, connection by name and connection by position. And initial begin. So first I am making clock equal to 1, d equal to 1, and reset equal to 0. So means I am making this reset equal to 0. Okay, I am applying reset equal to 0, and I am running for 200 time units. Dollar stop means I want to pause this reset, and I need to generate the clock. Always hash 5 clock equal to not of clock, and after 3 time units I am complementing d equal to not of d, and after 50 time minutes I'm again applying the reset equal to not of reset end module. Okay, like this also you can do. Okay, so this code I will execute. I'm opening Vivado. Just wait, it will open. So first you need to create the project, new project. Next, and I need to check the location. Um, which one? So one second. Training and development. One second. So I need to go to training and development, and the training and development, my digital and Verilog courses, and RTL G11 weekend batch, RTL course using Xilinx Vivado. Okay, this path you need to remember. And next, I'm creating the project. Okay, so I'm creating with project with sequential circuits. Okay, sequential circuits. I'm created the project. Next, and create the means create the file name. Okay, so my file name is let us take d flip flop only. Okay, so my file name is d underscore so d flip flop dff. Okay, same, you can use module name as file name. Okay, so just dff. Okay, dff, and go to this location where you want to store this codes. Okay, uh, so in this only I need to create so I need to store these codes. Okay, RTL using Linux Vivado, and okay. Next, this is optional only constraints. Next, I need to next and finish. My module name is also same. Okay, yes. So my module is my design source is created. Okay, so this code is there. No, this code, whatever the code I explained. So copy this and paste here, paste here, and save this file. And after that, go to simulations, add simulation sources for the test bench. Okay, simulation you need to write the test bench. Okay, so you need to store the test bench. My simulation source name is dftb, dfftb. Okay, copy this and create where I want to store. Choose the location. Mm, so store in sequential circuits only. Okay, finish, and d flip flop tb. Yes, my simulation source is created. Okay, dfftb. Okay, go to this code tb file. Just select all, copy, and paste here. So paste here and save. See here. So I wrote the instantiation. No, so that instantiation is means whatever the this instantiation is there, that came into this design instantiation is there, that came into this test bench. Okay, so this is under dfftb. Okay, and if you want to see the design, open elaborated design. Okay, how this tool is converting your code into gate level netlist. For all the sequential circuits, the test bench steps are equal only, same. Okay, you need to follow the 5 steps. Okay, those 5 steps, whatever the 5 steps I explained. So just remember, for the combination circuits, test bench steps are 4, and for the sequential circuits, test bench steps are 5. Okay. Mm. So you have if else statement, no? So if else statement means our this compiler is converted into this priority mux. Okay, different types of muxes are there, and here you have a D flip flop. Okay, Q bar. What are the outputs? Q and Q bar. Okay, so this is my schematic. Okay, that tool is converted into schematic. Okay, and next coming to the simulation, run behavioral simulation. So dollar monitor is not there, no. So it will not display. You can see in the waveform. Just a fit to page. So here, just to zoom this and drag this side. So here you see. Mm, so zoom this. Yeah. So here, 1 second. Yeah. So here, what happens when reset equal to 0? So here, the output will be in 0 only. Okay. When it will go into functional mode, when reset becomes 1, it will go into functional mode. Okay. So here, if you see. So that means when reset becomes 1. Okay. So during this state, mm, uh, so here during this passage of clock, whatever the q value is there, you are getting at the output. See here, q equal to d equal to what? D equal to 1. Okay. So d equal to 1 means you are getting q equal to 1. Okay. During this passage of clock, d equal to uh, d equal to 1, you are getting q equal to 1. Okay, during this passage of clock, d equal to 1, you are getting q equal to 1. Okay, and you need to see the clock. Okay, you need to see the clock, this clock. Okay, and during this passage of clock, d equal to so d equal to what? 0, it is going into 0. Okay, during this passage of clock, d equal to 1 means q equal to 1 only. Okay, so if you this set to fit to page, we can see this one. Okay, so when reset equal to 1 only, you are getting the output at q and q bar. Okay, just to complement, you are getting complement. Okay, during this passage of clock. Again, when reset becomes 0, what happens? All the outputs q becomes 0. Okay, so next during this, when reset becomes 1, so d equal to 1, you are getting q equal to 1 during this passage of clock, and d equal to 0, just it is following whatever the d input is there, it is following that. Okay, and in this code, suppose if I want to use mm, so if reset equal to 0, it will be reset mode, no. So if I want to use asynchronous active low reset, okay, this is synchronous active low reset. If it is asynchronous active low reset, what I need to do? Or neg edge of reset, I need to use neg edge of reset. Okay, I need to use neg edge of reset. If reset equal to 0, begin q equal to 0, q bar equal to 1, end, and else begin d equal to 0. Okay, else begin d equal to 0, begin. So q equal to 0. So 1 second. Yeah. So yeah. So you can see the simulation, run simulation, and in the test bench, how I given. First, I am making clock equal to 1, d equal to 1, and reset equal to 0, and I am running for 200 time units. Dollar stop, end. Always I am generating the clock. Always hash 3, d equal to not of d, and I am applying the reset after 50 time units. Okay, I am complementing the reset. So if you see this one, just expand this fit to page. So previously, when it is going from functional mode to reset mode, that is synchronous with the clock. Okay, just you observe here. Here, this is reset mode. When reset equal to 0, this is reset mode. Okay. So when it is going from one second. So when it is going from reset mode, so functional mode to reset mode, that is asynchronous with the clock. Okay, that is it will go into the reset mode independent of clock. Okay, so that is asynchronous of clock that you can see. Why? Because I given in the design that is passage of clock or negate of reset I given. Okay, so that is asynchronous with the clock. Okay, so this is about D flip flop. Is it fine? Do you understood the code? Any doubts or queries related to this D flip flop? Okay, I'll move forward. And next, coming to JK flip flop. So this is the code for JK flip flop. You know the JK flip flop. So that means truth table for the JK flip flop. So what is the truth table for the JK flip flop? Or first we'll see the SR flip flop. Okay. So SR flip flop. After SR we'll see the JK. Okay. So that means from SR, I think you are aware of digital. SR you will get D. Okay. From JK you will get T. Okay. So SR flip flop, if you see SR and Qn plus 1. Okay. How the truth table will be there? So this is 0 0 0 1 and 1 0 and 1 1. Okay. So when it is 0 0, memory state, reset state, set state and invalid state. Okay. This is the truth table for SR flip flop. Okay. D flip flop means anyway clock will be there. Okay. I'm not including the clock. Clock will be during passage of clock. This clock will be there. One more input clock is there. Okay. D means this is Qn plus 1. So if it is 0, output is 0. If it is 1, the next state value is 1 only. Okay, just it is following. That means next state equal to what? It is a sequential buffer. Whatever the input you are giving, you are getting into the next state. Okay, so this is SR truth table, and this is the D truth table, and JK means whatever the unused state is there. Okay, so in the SR flip flop, that is unused state is there. No, you are going to overcome in the JK. So JK just Qn plus 1. Okay, so 0 0 0 1 1 0 and 1 1. Okay, so this is uh, this is memory state, reset state, set state, and this is toggle state. Okay, whatever the unused state is there, you are going to use in the JK flip flop. Okay, this is JK. Okay, next, so how we will get the D flip flop means here from the SR flip flop, S and R are connected with an inverter. Okay, then you will get a D flip flop. Okay, so only these two cases I am using. If it is 0, you are getting 0. If it is 1, so that S and R are connected with inverter and you are giving one input. That is nothing but a D. Okay. From the JK, you will get T flip flop. Okay. So T flip flop how we are getting means J and K inputs are tied together. J and K inputs are tied together, and this input I am giving it to T. Okay. So that means you can use the only this state and this state. Okay. So if you see the truth table for T flip flop, so T and Qn plus 1, and if it is 0, memory state. Okay, memory state. If it is 1, toggle state. Okay, toggle state, Qn bar. Okay, if it is 1, that is toggle state. 1 second, yeah, toggle state. Okay, this is the truth table for the all the flip flop. Okay, so you need to remember this. So from SR you will get D, and from JK you will get T. Okay, so mostly like counters are there. Counters you will design by using JK flip flop, JK flip flop and T flip flop. That two operated in which mode means toggle mode, toggle state. Okay, and shift registers are there. Shift registers you will design by using D flip flops, D flip flops. Okay, and special counters also, Johnson counter and ring counter also you will design by using this D flip flop, and FSMs also you will design by using D flip flops only. Okay, there is excitation tables are there. So in the D flip flops, there is you are getting the D inputs that is equal to the next state only. Okay, so if you know the next state, you can see the D input, you can write the D inputs for the excitation table. Okay, so these are the truth tables for the SR flip-flop, D flip-flop, JK flip-flop and T flip-flop. So I think you are aware of digital. Okay, before coming to this RTL design, you should be aware of this digital. Okay, digital design. And first we will see the SR flip-flop. SR flip-flop is not there. Okay, SR flip-flop you try. Okay, JK flip-flop I will tell you. See the JK flip-flop. Just yeah. Module JK. What are the inputs? JK reset, JK clock reset Q and Q bar. Okay. Input. What are the inputs? JK clock reset. Output. As this is a behavioral modeling, I need to declare the output with reg data type. Output reg Q and Q bar. Always at the rate passage of clock. This is synchronous reset. Okay. This is a synchronous reset. Okay. Both functional mode and reset mode is synchronous with the clock. Okay. Begin. If not of reset, begin q equal to 0. That means when reset equal to 0, q equal to 0 and q bar equal to not of q. And else I am using if else statement. Okay, I can use the procedural statements, no. So that we already discussed in the behavioral modeling. Procedural statements are if else statement, case statement, and while, for, repeat, all those statements. Okay, if j equal to 0, k equal to 0, begin. It will be in which state? Memory state. Q equal to q and q bar equal to not of q. And else if j equal to 0 and k equal to, I am using relational operator and logical operator. Okay, we already discussed the operators, no. So I am using the logical equality operator. This is logical equality operator. Okay, so logical equality and logical and operator. Okay, so and k equal to 1. So it will be in which state? Reset state. Begin q equal to 0, q bar equal to not of q. End. Else if, okay, j equal to 1, k equal to 0. Okay, begin q equal to 1, q bar equal to not of q. Okay, and else begin. So what is the other state? So no need to write. That is 1 1 only. So q equal to not of q. This is a toggle state, and q bar equal to not of q bar. This is q bar equal to not of q. Okay, q bar equal to, here, one second. Q bar equal to not of q bar. This is not of q. Okay, not of q. Okay, and not of q. Yes, not of q. And end module. Okay, so is this code is fine? Do you understood? Based on the truth table only, I am writing this code by using if else statement. Shall I move forward? Anyone give response so that I will move forward. Yeah, hope you understood. Next you see, I need to write the test bench. Okay, so module jktb. So whatever the variables for the test bench, q and q bar, I need to declare with y data type, and clock reset and jk. These are the variables for the test bench. Okay, so, so I need to declare with reg data type. I need to instantiate jk, and instance name is dut underscore instant jk. So how you declared in the design, the same model you need to declare in the position. This is instantiation by position with the order list. Okay, and next you need to generate the clock. Always hash by clock equal to not of clock. Initial begin dollar monitor. Okay, as I told you, like Verilog event scheduler, dollar monitor and dollar strobe, that will be available in the last mode. No, okay, so whatever the last updated value, that will be updated in the dollar monitor and dollar strobe. Okay, we already discussed and you have active region, nba region. Okay, and all those things are there, no. So that's why I'm first of all I'm using dollar monitor. So dollar monitor is nothing but if there any change in these variables, then it will display. Okay, so this is a dollar monitor, and I'm giving clock equal to 1, reset equal to 1. When reset equal to 1, I am making j equal to 0 and k equal to 0. Okay, and I'm running for 35 minutes, and after that I am making reset equal to 0. And so in the code, if you see the code, I'm closing this d flip flop and close it. If not of reset, if reset equal to 0, output should becomes clear, no. So I'm making reset for 35 minutes. After that, I am making j equal to 1, k equal to 0. After 30 time minutes, I am making j equal to, you can give 10 also. Okay. J equal to 0, k equal to 1, and 30 time minutes, j equal to 1, k equal to 1. I will run for 250 time minutes and dollar stop. Okay. So this is my test bench. So if you want to run in the Vivado, just add the design source. Next, create the design source. So what is my design source? JK. Okay. JK is my design source. JK. Okay. And finish. Okay. Yes. Module name is also same. This is JK. So this code is there now. So this is my JK flip-flop. So copy here. Copy this and paste here. Save this. Save this. And go to the simulation and create the simulation. Create the file. What is my module simulation? JKTB. 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 Okay. Finish. Okay. Yes. And my simulation file is created. So just remove this, not required. And this code, select all, copy and paste here and save this. Now this JK dut underscore instant is there, no? That instance name and JK is instantiated under JKTB. Okay. So if you want to see the design, you need to right click, set as top. This also right click, set as top, set as top. Okay. I want to see the elaborated design. Open elaborated design. Yeah, this is the tool converted your code into schematic. Okay, this is the schematic design. Okay, you used if else statement. No, if else statement means you are getting some muxes. It will be converted into 2 cross 1 muxes. Okay, at last it is converted into D flip flop. See here. Okay, so this is tool is converting into schematic and next run behavioral simulation. So whatever the module you want to simulate, you need to right click and set as top module. Okay. So you given the dollar monitor, no? So dollar monitor. So when j equal to k equal to 0, q equal to x. J equal to 1, k equal to j equal to 0, k equal to 1, q equal to 0, j equal to 1, k equal to 1, q equal to 0. That we will see this see in the simulation. So fit to page. So initially when you are applying the reset, it will be unknown only. Okay, q and q bar are unknown only. And during this passage of clock, so you are making reset equal to 0. So during this state, one second, one second. So in the code, when reset, not of reset, q equal to 0, no? Okay, one second. So first you need to make reset equal to 0, and after that I need to make reset equal to 1, and first I want to execute in 10 time minutes. 10 time minutes. Okay, save this. And if you want to relaunch the simulation, this icon is there. Just to relaunch the simulation. So see this fit to page. Yeah. So here if you see, uh, so when reset equal to 0, q equal to 0 only you are getting. Okay. And when reset equal to So when reset equal to 1, it will go into the functional mode. So during this passage of clock, I am searching for this j equal to 1, k equal to 0. It will be reset. It will be set mode. Okay, and j equal to 0, k equal to 1. It will be reset mode. And here j equal to 1, k equal to 1 means what? It will be toggle mode. Okay, goes on toggling. See here, goes on toggling. It goes on toggling 0, 0, 1, 0, 1. Every clock cycle it will goes on toggling. Okay, every clock positive edge trigger clock cycle it goes on toggling. Okay, so like this you can analyze. And next hmm, so you need to execute for suppose 50 time minutes. 50 time minutes. Let's relearn the simulation. Okay, we'll get 50 time minutes. This is the square 50 time minutes. We'll getting when reset equal to 0, both are q is 0 only. And when reset equal to 1, it will be functional mode. And so during this passage of clock, j equal to 0, k equal to 1, it will be 0 only, reset mode. And j equal to 1, k equal to 1 goes on toggling. And during this passage of clock, the j equal to 1, k equal to 0. Okay, it will be set mode. Okay, this is set mode. Okay, so this is about the JK flip flop. And coming to the T flip flop, so this is T flip flop. So T flip flop. So here you see module T flip flop. What are the inputs? So this is method one. You need to declare the port list, and after that separately you need to declare the inputs and outputs. This is style one. Okay. Style two means you need to declare the inputs and outputs within the bracket itself. Okay. So T comma clock comma reset comma Q and Q bar, and you need to declare input T clock reset, output range Q and Q bar, always at the rate passage of clock. Begin. If reset equal to 0, you are resetting the output. Q equal to 0, Q bar equal to 1. End. Okay. If multiple statements are there, you need to write between the begin and end. Else begin. Q equal to what? Not of T. Q bar equal to T. Okay. So that is toggle state. You are getting toggle state. Okay. So Q equal to not of T and Q bar equal to T and end module. Okay. So this is my code. And coming to the test bench, so here you see. So first, the test bench. First, you need to declare the test bench, and Q and Q bar we need to declare with Y data type, and T clock reset we need to declare with reg data type, and next. Uh, so here T flip flop DUT. So you need to instantiate this design. Okay, T clock reset Q and Q bar, and next you are generating the clock. Always hash by clock equal to not of clock. Okay, and second. So next initial begin. You need to declare. You need to initialize the reg variables. Okay, here there is a mistake in this. You need to initialize the reg. What are the reg variables? Reg variables are T clock and reset. No, you are initializing the reg variables, and initial begin. I am making clock equal to 1 and T equal to 1. I am deasserting the reset. Okay, deasserting the reset means I need to make reset equal to 1. Okay, reset equal to 1, and end initial begin dollar monitor. Okay, if there any change in these inputs, then it will execute. So for 50 time minutes I am making reset equal to 1 at the rate passage of clock. Okay, T equal to 1 tick binary 1, and at the rate passage of clock, so whether I am checking uh, toggle state. Okay, toggle state during this passage of clock or not. Okay, so okay, yeah. So here this code T flip flop. So T flip flop. So go to sources, add this file, create design source. Next, create, and my file is T flip flop, and choose the location sequential circuits. sequential circuits, and OK, finish. And my module name is also T flip flop, T flip flop. OK, select all, copy, and paste here. Save this file, and go to simulation, add simulation. Next. So what is my source? Simulation source. Simulation source is T flip flop TB. Create file T flip flop TB. Choose the location. Sequential circuits. Select OK. Finish. OK. Yes, module name is also same thing. I want to say. And T flip flop TB. Just remove this. Delete. And this file. Select all. Copy. And paste. Save. Now my code is instantiated. My design is instantiated under this T flip flop. So I given this instantiation, no? Connection by position, and I want to see the design set as top, and this also I want to see the design set as top. I want to see the design set as top, and next elaborate the design. So the tool is converted your code into like this gate level netlist in terms of muxes and D flip flop. Okay, mostly it will be in terms of D flip flop only. Based on your if else statement, it is converted into 2x1 mux. Okay, so this is elaborated design, and coming to simulation, run behavioral simulation. So you can see the outputs also. So when q equal to 0, t equal to 1, q equal to 1, t equal to 0, toggle state. Okay, so here, so fit to page. So during this, when reset, one second. Rerun the simulation. So when reset equal to 0, so q equal to 0 and q bar equal to 1 only. And when reset equal to 1, so when t equal to uh, so when reset equal to 1, when t equal to t equal to 1, so during this state t equal to 1, so during this state when t equal to 1, the q becomes 0 and q bar becomes 1, and when during this state uh, so when t equal to 0, q becomes 1 and q bar equal to 1, q bar equal to 0. Okay, so that means when q equal to, so when t equal to 0, it will be in which state? So it will be in the previous state only. Okay, memory state. Okay, when t equal to 1 means it will be in the toggle state. Okay, it will be in the toggle state. So like this you can see the output for T flip flop. Is it fine? Any doubts or queries in this? Synchronous counter also you can see. See here, synchronous counter. Synchronous counter you have synchronous counter. So what is the difference between synchronous and asynchronous counter? Synchronous counter is nothing but a common clock is given to all the flip flops, and asynchronous counter is nothing but the output of one flip flop is acting as a clock for the next flip flop. Okay, so if you see the synchronous up counter, so this is a 3-bit synchronous up counter. Okay, so if you see, hope you know the synchronous up counter. So module synchronous counter up, input clock, input reset, and output reg 2 down to 0. So I am using a vector count. Okay, always at the rate passage of clock or neg edge of reset begin. If not of reset, count equal to what? 3 tick binary 0 0 0. Else count equal to, you need to increment the counter. Okay, count equal to, count is non-blocking with count plus 1 tick binary 0, binary 1 and end and end module. Okay, this is my design. Okay, and coming to the test bench, TB synchronous synchronous up counter. This is the test bench. So first synchronous up counter. So first module synchronous up counter TB declare the internal variables. Okay, reg clock, reg reset, and wire 2 down to 0 count. And this is nothing but instantiation. Okay, connection by name. Okay, synchronous counter up. Instance name is UUT. So whatever the variables outside the bracket are nothing but design inputs and outputs. Whatever the variables inside the bracket are nothing but test bench inputs and outputs, input test bench variables. And next you need to generate the clock. So clock generation, initial begin, clock equal to 0. So initialize the clock. First you need to initialize the clock. You can use, I told you, you can use forever. Okay, hash by clock equal to not of clock end. So create a clock with 10 time units, period of 10 time units, and generate the stimulus. Okay, so reset equal to what? 1 tick binary 0. Okay, I am applying the reset for 10 time units. Okay, so this is asynchronous active low reset. Now in the design I already showed, that is synchronous counter. See here, always at the passage of clock or neg edge of reset. Okay, asynchronous, if not of reset I am making the output to 0. Okay, and next you need to generate drive the stimulus. So initial begin, I'm applying the reset. Reset equal to 0. I'm for 10 time minutes, and I'm desetting the reset. Okay, and I will run the counter for how many time minutes? How many clock cycles? 8 clock cycles. Okay. Yeah, let us take each clock cycle is 10 time minutes. Now I created the clock, and again applying the reset again. Okay, for 10 time minutes and end simulation. Okay. So this is optional only. If you want to see the outputs, I can use the initial begin dollar monitor. Uh, uh, time. Time percentage b percentage d dollar time reset count. Okay. If you want to see the waveform in EDA playground, you need to use one more two more commands. That is a dump waveform data for viewing the simulation tool in EDA playground. Okay. So here this one I am creating. So just copy this code and create the design source. Create the design source and so select the choose the path sequential circuit. Select OK. Finish. OK. Yes. What happened? Add the design source. Next, create this source. So what is my synchronous count? Synchronous counter. Synchronous up counter. Copy. Paste here. Choose the location. Sequential circuit. Yes. Okay. Already existed. One second. It's not created. Okay. I will create one more project. Create new project. Next, I'll create counters. Okay. Next, create the file name. So what is my file name? Synchronous counter. copy and paste here. Okay, next, 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 finish. Yes. Okay, my module name is also same, synchronous counter, and this code is there now. So select all, copy and paste here. This is a time scale and precision. Okay, so time scale is nothing but that the waveform will be each the time period is, that is nano in terms of nanoseconds, and precision is nothing but so if it is in decimal, like decimals, it is round up to nearer value. Suppose 10.56 or 10.75, like that, or 9.75, like that is, then means it will round up to 10 time units. Okay, I'm saving this file, and next coming to the test bench. So what is my test bench name? Synchronous up counter TB, copy, and you need to create the simulation source. Next, create create the simulation source. Choose the location. Uh, Sequential circuits only. Okay, finish. Okay, yes. So next, my simulation source is created. TB file is created. Just select all, copy, and paste here. So by simulation source, this is UT synchronous counter up. Okay, created. Okay. So if you want to design, see the design, open elaborated design. Open elaborated design. So this is converted into counters. See here. So plus is, it is adding. It is in terms of D flip flops only. So three D flip flop, four D flip flops. So here, so D flip flops, in terms of D flip flop, it is created, and it is, there is a adder circuit. Adder is there. Okay, every time it is adding, and inputs are reset clock at the input. Okay, and the count output. That is zero down, two down to zero means 3 bits. Okay, it's three. So 3 bits means we are using three flip flops. Okay, so this is a schematic, and coming to the simulation, just run behavioral simulation. Run behavioral simulation. Dollar monitor means it will count. See here. Dollar monitor means it is executing the TCL console. So reset equal to 0, count equal to 0 only. When reset equal to 1, it is counting from 0, 1, 2, 3, 4, 5, 6, 7. Again it is coming to the initial state. Okay, have you observed this? So that is this is a mod 8 counter. The counting states are from 0 to 7. Okay, again it will come to the initial state. Okay, so you can see in the waveforms also. So just open this and fit to page. See here. So when reset equal to 0, so what will be there? When reset equal to 0, output will be 0 only. Okay, and when reset equal to 1 only, it starts counting. Okay, during this passage of class. Okay, count will be incremented. Okay, so output count will be incremented. Okay, and after 7 again it will come to the initial state. Again you are resetting the device. Okay, so if you want, you can see in the binary also. Go to radix and click on binary. 000 001 010 011 100 101 110 111. Again it will come to the initial state. Okay, so this is the up counter. Okay, so we'll see the down counter and we'll wind up. Okay, discard. Okay, just it is asking for saving. Okay, so coming to down counter, this I will close. Just it will count from top to bottom. Okay, from 111 to 000. Okay, so synchronous counters, RTL. This is down counter. Okay, decade counter will discuss tomorrow. Just you see here. Uh, so module synchronous down counter, input clock reset and output range 2 down to 0. Always at the rate passage of clock or negate of reset. Begin. If not of reset, count equal to 3 tick binary 000, else count equal to count minus 1 tick binary 1. So it will do the down count. Okay, it will do the down count. Okay, and next coming to the test bench. This is test bench. Okay, synchronous down counter. Okay, synchronous down counter. So here you see the module. My test bench name is synchronous counter down TB. So you need to declare the internal variables clock and reset with edge and count 2 down to 0 with wire. Okay, 2 down to 0 count with wire, and you need to instantiate connection by name. My instance name is the UUT, and you need to generate the clock. Clock equal to 0 forever. #5 clock equal to not of clock with time period 10 time minutes, and you need to apply the reset. You need to assert the reset, and you need to release the reset and apply the stimulus. Okay, reset equal to 0, you need to run for 10 time minutes and end the simulation. Okay, simulation and monitor. Dollar monitor means you can see. Okay, you should run when reset equal to 1, the count should happen for 8 clock cycles. Okay, 8 clock cycles. After that you need to make reset equal to 0 for 10 clock cycles. Okay, so this one, so just save this, this copy this again in the Vivado. So create the design source, create my file name, choose the location, yeah, sequential circuits only. So yeah, sequential circuits, okay, finish and down counter, yes, yes, again synchronous down counter. So select all, copy, and here you paste, save, and go to simulation, add simulation source, create simulation source, create. So what is my test bench file? Test bench file is synchronous counter TB. So copy this and save. So choose the location where I want to save synchronous sequential circuit. So okay, finish, okay, yes. Synchronous counter down counter my created. Just select all, copy. So it is better to write the comments for each and every instruction. So you can understand the code easily. Okay. So save this. Now in the down counter, I instantiated now. So that is instantiated with this instance name. Okay, that is UUT synchronous. So what is my design name? Synchronous underscore counter underscore down. Okay. So if you want to see the design, right click, set as top, and this design also set as top. You want to see the simulation, you need to set as top, and you want to elaborate the design. Same steps only. Elaborate the design. You got the counter. Here mine is subtractor, RTL subtractor, and it is converting into 3D flip flops. Why? Because count 2 down to 0 count, no? Okay, so reset the clock and count to 2 down to 0. Okay, so the RTL, so this they give it is given the name RTL reg asynchronous. Okay, so just I want to see the simulation, run behavioral simulation. So in the TCL console also you can see. So when reset equal to 0, count equal to 0 only. When reset equal to 1, it will start from count 0. 0, 7, 6, 5, 4, 3, 2, 1. Again, it will come to the 0 position. This is mod 8 down counter. And again, when reset equal to 0, count equal to 0 only at 90 clock cycle. You can see in the simulation also. So if you see the simulation, just fit to page. So it will start from, so when reset equal to 0, the count equal to 0 only. Okay, this is the reset equal to 0. So when reset equal to like when reset equal to 1, during this passage of clock, it will start from 7. 7 and next is 6, 5, 4, 3, 2, 1 and 0. Again, it is going into reset mode, no? So that means irrespective of clock, it is going to, this is asynchronous active low reset. So irrespective of this clock, it is going into the reset mode. Okay. So this is asynchronous active low reset. You can see in the binary also. Go to radix and see in binary. So initial state is 0, 0, 0 and it will start from 1, 1, 1, 1, 1, 0, 1, 0, 1, 1, 0, 0, 0, 1, 1 and 0, 1, 0, 0, 0, 1 and 0, 0, 0. Okay. So like this you can analyze the uh, synchronous up counter and down counter. Okay. Is it fine? Any doubts or queries?